I'm Michelle Frisbee.
I'm Uchan Shin.
I'm James Grau.
And I'm Kenton Anderson. We are Team 18 and this is our DP3. Our project is called Units, Conductors, and Volume, and our group is Fun Creative Learning. So far our project's gone through 4 major steps. We've gone through project management where we planned everything out and got customer interviews and information from our potential customers. Then we went into concept development where we got our target specifications, our concept generation, and our product decomposition. We basically developed what we were going to make, and then we went into the actual design fit stage where we designed our product and got a real solid design down for it. We did a failure mode effects analysis on it we did an environmental analysis, and we got a final architecture designed. Once we had a prototype developed, we went into economic analysis where we checked our break-even point, decided what we would need for investments, and decided what it would cost and how long it would take to actually develop this product. And then later in this presentation, we discussed the future plans for this product.
At the beginning of the project, our team devised a schedule on a Gantt chart, and we've followed that. Although at one point we had to make adjustments, and we changed prototyping and intellectual properties to be parallel tasks, which gave us more time for both, and still kept us on schedule. And we've completed the following tasks on time and are currently finishing our very last one, which is the final presentation. First in this project, we gathered customer needs, which were taken from interviews and customer profiles and use cases. And one of the most common, this is a sample of the most common customer responses to an interview. And one of the most important ones that came up was that it teaches and enforces the learning topics.
Based off customer needs, we were able to get product specifications that the design of the BRG would be based off of. Our most important product specification was that it had a number of obstacles. This is because a higher number of obstacles will allow to teach the learning concepts better, which is our most important customer need. The customer needs can be seen here. They're ranked in order. Over there you can see based off their importance, the most important being that the BRG teaches and enforces learning concepts. Here, the higher the number you see in this part of the chart is how they relate to the specification in that column, as you can see right there.
We generated concepts and created different combinations of them for like this chart. We went through a concept selection process which included screening and scoring, and our ending concept was this. It includes a combination of diameter conversions, finding the volume of a cube, and connecting and completing a circuit to run a conveyor belt.
So for the product decomposition, those black boxes indicate the flow of energy, the movement of the ball, and when the Arduino motor will be triggered. The overall box demonstrates the inputs and outputs of the machine, and 3 different types of lines represent detail sources that help the ball to go through the obstacles. These black box diagrams are significant to recognize how the energy flows through a product and apply it on the object to successfully overcome each obstacle.
Alright, so then our team went on to doing a benchmarking table and an intellectual property table. From doing these tables, the main thing we noticed is that our product has a real advantage over the market because it really combines the idea of having fun with the idea of like gaining some educational value. As you can see, the one we have on here is Monopoly, and Monopoly was much more targeted towards the having fun side of things and kind of gave up on the educational value. They claim to have some, but as you can see, it's more visually appealing than it is an educational thing. And that's the last thing we got from doing these tables, is that we also decided our product needed to be a lot more visually appealing if we wanted to have any chance in the market.
So one of our biggest goals and also a product specification of ours was to have as few parts as possible. As you can see from this CAD, this pretty much shows a mock-up of our entire BRG, and it points out some of the major components, actually all the major components of the BRG. There aren't very many, as to stay within the goal of having as few parts to the BRG as possible. And we wanted to make it simple to assemble, simple to take apart, and simple to move around. So here are some other CAD views of some major components of the BRG. These are more 2D views. Our most complex part of the BRG was the conveyor belt obstacle. Two 2D views of it can be seen here. This is the base of the conveyor belt obstacle, and then it would have two wheels which attach to these parts right here, and then the conveyor belt, which can be seen here, would slide onto those two wheels. And that obstacle is meant to represent the conductivity section of our BRG.
The next thing our team did was a failure mode effects analysis, and we realized that the highest RPN chances are that the user that gets the device is going to construct it improperly. Our device is pretty tricky with putting everything together perfectly, and with small mistakes it'll cause the ball not to flow through the device. Though it's not a super severe thing, it is definitely the most likely to happen, and it's definitely the hardest to detect. And the recommended actions that our team decided is that when the project actually goes under development, we would essentially beef up the connections and make it impossible to plug them in the wrong way.
Environmental considerations are important for any product, from both external and internal pressures. One of the biggest changes we found that we could make in our product came from the materials we used. The current design uses a lot of cardboard, which causes deforestation, and also all the connections in our project were duct tape, as seen in this picture, and that ends up in landfills. So one of the main changes we decided to make was to change all the connections to metal screws or joints so they can be reused afterwards and don't end up in a landfill.
So the product architecture is designed to represent the team's understanding of the constituent elements of the BRG product. 3 obstacles are split up per function as shown here. Arduino sends signals to the motor in the fuel, which gets energy from a DC 9-volt battery. This lifts the ball by the conveyor belt and deposits the ball into a ramp. When it reaches the top of the machine, from this ramp, the ball goes over a half tunnel that must be filled with sand. And for the last chunk of product architecture, a tunnel that is controlled by a knob stands between the previous obstacle and the end of course. So our team used industrial design techniques to evaluate the aesthetics and ergonomics of the FCL BRG machine. From the figure above, the product performed the best in the categories product differentiation and appropriate use of resources. This is because compared to the other learning tools, the goal of the FCL machine was to be clearly unique and special. And materials were chosen for durability and manufacturability in order to overcome chances of failure and to meet environmental regulations.
So one of the last few things our team had to do was analyze the time and cost that it would take to develop this product if it actually went into mass production. And the main thing we noticed from both of these charts is that creating the body of these, which we decided we would have molded out of plastic, is going to be by far the most time consuming and expensive thing that we're going to do with this project. Everything else that we would get would essentially be purchased pre-made, for example the Arduino, and wiring it up and getting the ball set up and putting sands in the cup. All of that stuff just has about total cost around like $5, and then you can see the part assembly time is very low as well. And then just compared to the body of the obstacle, it's almost twice as much for the cost of everything else. So the main thing we decided is that if there's any way that we can make molding plastic cheaper or faster, that would greatly benefit our project.
So economically, it was decided that our project was going to cost $50. This was based off the cost to manufacture and pay employees, as well as other various costs of the project of $30, as well as the need to pay our investment back within 2 years. Our investment was about $500,000. This was decided based off the need to pay employees, as well as various startup costs and manufacturing costs while we weren't really making much money and while the product was still taking off. It can be seen through this chart that after about 501 units are sold, we will break even and start to profit greatly. And we decided that at that time, or after 4 quarters, as you can see here, we won't be paying our loan back until the 5th quarter. After 4 quarters, we should be able to sell 501 units, and therefore we will break even, and we'll be able to have the funds to start paying back our loan.
We've analyzed a lot of the design so far. However, in the future, we still need to run stress analysis on many of the parts to see the lifetime and usage of the conveyor belt, for example. And the structure holding the conveyor belt also has a lot of stress put on it due to the weight. It holds. So improving the design so they can be more durable and last longer and increase the lifetime of the product. This would also decrease waste. And we would also look into manufacturing processes for ramping up production and manufacturing the product widely.
So in conclusion, if our product ever went to mass production, we noticed that the main thing we need to put time into is the development of the body pieces, trying to make it cheaper and faster to mold them out of plastic. We also noticed that the most likely failure of the project is for it to be constructed improperly, which makes us want to, at some point, go back and redesign the attachments of each piece. And when we prototyped the BRG, we used entirely environmentally friendly materials, as you can see in the picture. It's mostly made out of cardboard. And lastly, through all of our economic analysis, we decided that if it did go into mass production, it would be being sold for $50.